Thanks everyone for really nice welcome, and thanks to the organizers for inviting me over here. It was a very long journey from New York to Seoul. So what am I going to talk about today is basically different aspects of what I'll try and do is cover some of the success stories that I have been involved in directly, and talk about some of the research challenges that are missing when it comes to handling large volumes of spatiotemporal data, especially in the wild. And before doing any of that, I'm going to do a shameless plug, which is ACM Census 2019 is in New York this year. So I know that the paper deadline has passed, but please, you're welcome to come and attend. And it's going to be a fantastic event. I'm, by the way, general co-chair, so I get to do the shameless plug before I begin my talk. So, having said that, what I'll do is to start looking at what has changed in the last 10 years in terms of location data. If you think about it, location became very accessible. You have your smartphones that send location data. Okay, so you have your smartphones that send location data, and you have so many different devices that are sending location data. And also, if you look at in the wild, in outside, not just your smartphones, there are so many other sources of location data which is dramatically increased in the last 10 years. And to begin with, first, one of the things that we have looked at is this Port Authority of Singapore. And it's very interesting that if you go on to what is called as AIS beacon data, these are location data generated by ships, and they have to share it publicly because of interest for tracking ships, making sure there is no illegal activities being done. So Singapore Port Authority approached us saying, hey, can we today, I mean, this was about 5 years back. 5 years back, they had coast guards and people staring at large screens, staring at radar screens, trying to figure out which are the possible ships that are involved in illegal activities. It could be drug trafficking, human trafficking, and so on. And the challenge there is that Singapore, being the world's largest port, has several thousands of ships that come every day into the port and several millions of containers. I'm sure if Rajesh is in the audience, he will tell you about all of Singapore Port Authority. So the question is, how do we go from that system, which was, oh, there, Rajesh, you're here. So the question there is that how do you augment the intelligence of the Coast Guard by pointing out which are the ships to look at. So when the challenge here is, many ships are coming in, and you want to know which routes are sort of anomalous. And anomalous is a very vague definition. I mean, there is several statistical definitions of anomalies. And here the question is, how do I know which ship is involved in any illegal activity? So we created some of these foundational pieces, which were what we term as blackouts and hangouts, and try to identify patterns which can lead towards possible bad behavior. So you might say, what are these anomalous behaviors, right? And again, my aim is not here to go into depth into any of these use cases. That I'm happy to take offline questions and we can have discussions about it. But the goal here is to talk about some of the key challenges that arise when you're dealing with, say, large volumes of spatiotemporal data. And so here, there are some very interesting challenges that are posed. For example, what might happen is that a ship typically ships have well-defined routes when they're going into the ports, and they can deviate from them because of numerous reasons. One could be the amount of traffic that is going in, or other could be just weather and bad conditions in certain channels. So you might change the channel. So that does not necessarily make it an anomalous behavior just because a ship is deviating. And there are other interesting examples where a ship is sending out its AIS beacons, and many times this ship switch off the AIS beacons due to several reasons, they're malfunctioning equipment, or they just somebody forgot to switch on the AIS beacon. And even though the ship is being tracked using radar, the question becomes, is this ship demonstrating malicious behavior, or is it actually something else that was happening? So how do you start differentiating all of these patterns and then be able to say, in say the several thousands of ships and several encounters that are happening between multiple ships, which ones are really demonstrating malicious activity? So I think just a brief summary of what we did there is that when we deployed our solution in the Singapore Port Authority, year over year, this is I think a picture from one of the conferences of IBM. Year over year, we had a reduction of 17% in trafficking scenarios. The next one is a little bit more fun. This was an activity that we engaged with University of Hawaii and NASA's JPL. And the question here, if you look at asteroids and asteroid belts, there are roughly 700,000 asteroids known today to us as humankind. And the number of asteroids being discovered on a daily basis is dramatically increasing. I mean, several new, I think 100 asteroids per year are being identified. And there is a very interesting problem that the University of Hawaii posed to us, which was the question of saying, today we are able to track asteroid location using a certain physics model, which says which takes into account only they have 9 planets, even though we do not have 9 planets today. So they have 9 planets in their model, and they try to say, okay, where will this asteroid be, say 1 year from now, 5 years from now, and 10 years from now. But what it fails to account for is when 2 asteroids cross each other's paths, we do not really know when that happens. And the problem that 2 asteroids crossing each other's paths creates is that even when they fly by, they define a close encounter between 2 asteroids as anything between 1,000 kilometers between those asteroids. So anytime these asteroids come within 1,000 kilometers of each other, what happens is, depending on the size and the constituency of this asteroid, they can deviate their path. So even something like a 0.001 degree deviation in their path over the course of next 5 to 10 years can result in 1 million kilometers deviation from the asteroid's path. And 1 million kilometers might mean striking the Earth versus not striking the Earth. So NASA has this very nice website called NEOS. They call it Near Earth Objects Tracker, which continuously tracks which objects like asteroids or any other foreign objects are coming close to the Earth, so that you can take evasive action. So it so happened, I think in 2011 or so, that by chance someone encountered 2 asteroids collide with each other, and then one of them emerges as a split asteroid, and then it separates out. And there is a nice image which I'm not showing over here. But the problem there is that if you start looking at a simulation, so even with 9 planets taking into account, it takes several, say, hours to simulate how far, where is the location of these asteroids into the future. So every day they're monitoring several of these asteroids in the space and then adjusting their future computations and orbitals elements based on those computations. Now, if I introduce 700,000 asteroids into this computation model, it would take several millions of hours, even on some of the best compute environments, to even compute for a single asteroid's location for 25 years. So what this boils down to is there anything we can do from a spatiotemporal standpoint? Can we reduce the computation required by combining a 3D spatial indexing mechanism along with the physics models that are used for simulation? So basically what we did was to create a pruning mechanism to identify, combining it with the physical models to be able to say which asteroids should we be looking at from a close encounter perspective, and which asteroids we should not be combining. So think of it like a pruning technique, but that takes into account the physics models as well as the spatiotemporal locations. And what we did was, in collaboration with University of Hawaii and NASA's JPL, we developed a 25-year prediction of all asteroid encounters. And it so happened that a year and a half before our prediction, when we share it with the University of Hawaii, they, that was the closest in time prediction, which was meaningful, was a year and a half into the future. And University of Hawaii sort of positioned the telescope into the space for this particular, trying to observe this particular event. And this is an email that we received, like sort of a eureka email saying this is the first time ever that they have observed two asteroids come close to each other. So the funny story here is that when I got initial when I got the initial email, these two arrows were missing. So I looked at this image and said, hey, what does this even mean? This has no meaning. I understand the enthusiasm in this email, but I don't understand it. So being the computer scientist here and not an astronomer, I had asked them, can you please point with an X mark where these asteroids are? And they came back with these two X marks. And the distance between this is roughly, 1,000 kilometers or so. Which actually qualifies, as per their definition, a close flyby, and this was the first time that they encountered it. So it was presented in what is called as, I think it's called AASDPS. I don't remember the exact acronym's expansion, but it is their premier conference in astronomy for reporting observations about new things that they have discovered. So again, the point here, I think what I'm trying to drive towards is that when you start looking at in the wild IoT devices and things that are monitoring, in this case, these are large telescopes that are gathering information on a daily basis. You can go, these are public data sets, you can just go download, all these asteroid locations today, and you can keep updating them every day. The challenge is to be able to combine information from other sources. In this case, it was physics models. In the previous one, it was taking the information from humans who have learned different shipping patterns and then being able to encode those patterns in creating a model. So it's a non-trivial encoding, because when you're talking to someone who is looking at these radars in the previous example, it's not that I know that this particular pattern is resulting in is an anomalous pattern, is a bad behavior. It's sort of, I wish I could find out if these two started co-locating with each other and then started moving away, and then there's one ship that forks off from it. That's a possibility. So taking all of those information, taking extraneous information into account becomes a key question. So more recently, in the last year, we have been looking at protecting rhinos in the well-governed game reserve. So this was a very interesting problem, because what started off as the initial simple thing is like, hey, why don't you put a tag on a rhino, right? And start tracking it and then look for behavioral pattern changes. But the challenge with it is twofold. One is if you are tagging a rhino and if it changes its behavior because of a poacher, then it's too late. I mean, you have a very large area that is being covered and you have to deploy rangers to protect these rhinos. You are probably not going to catch the poacher in time to protect the rhino. And the second is the location of the rhino is very well known now. And it so happened, so this was the first thing that we did in the beginning, and it so happened that some of the people were selling the location of the rhino for profit. And this is a true story, and it was among the, I think it was one of the key political figures that was actually selling the locations. So now it became a question of, is there a better way of, handling this? And we started working with animal behavioral scientists who said, a standard one could sort of, again, this is all in a completely different domain, and we don't even speak the same language as these behavioral scientists. So what they said was, hey, why don't we tag the large herbivores around the rhinos, which act as sentinels in some ways, and if you can basically say, their behavioral patterns and behavioral changes can identify poachers beforehand. And they are also very similar to the rhinos. But what happens is it poses a very tricky problem, because unlike rhinos, which have no predators whatsoever except us, humans, things like zebras, impalas have predators. And just because a zebra or impala is running does not necessarily mean a poacher is attacking it. And which basically says our standard models where you can say, let me just deploy something which will identify running, or let me deploy something which will identify that this animal is moving in a weird way. It does not necessarily work in this case because it does not mean it's a poaching attack. So what is the challenge here is are there fundamental differences in the animal behaviors when it comes to poachers versus predators? And when we spoke with animal behavioral scientists, they said, yeah, generally speaking, when poachers are attacking the animals, they tend to form a single file and run away from the poacher, whereas when a predator attacks the animals, they tend to do a scatter. And I think you can relate to this because that was the first time I was like, oh, that makes sense, because I saw all these things in Discovery Channel growing up saying, oh, when a predator attacks, you can see a nice scatter formation. And it is, again, validated through a lot of experiments that behavioral scientists did, or people working for Nat Geo and BBC, Planet Earth, and so on, who have observed these animals over long periods of time. But at that time, there was no IoT devices monitoring them. Now there are IoT devices. So we tagged roughly 120 or so zebras and impalas and so on, like 4 different animal categories. And I would say, a fairly large game reserve, this is the well-governed game reserve, and tried tracking, identifying poacher behaviors. So here, again, the challenge is that you don't get labeled data. Like, today, say something like Google or Facebook can come up with a ton of labeled data for all different kinds of images and so on and so forth, right? But here it's very difficult to get labeled data. You can get, with great difficulty, you can get validation data. So we did work with the game reserve people who created poaching simulations, where in fact they took a chopper, they went out and they shot at the animals with blank rounds to simulate a poacher behavior, so that we can see if our models can predict that there is a poacher. So there is I know that there is a paper that we have written. We haven't published it because of, I would say, legal reasons. We could not publish anything on top of this data set, unfortunately. But we've been able to show that with 85% accuracy on the validation data set, using this, again, input from the behavioral scientists about the scatter patterns versus a single file pattern, we were able to identify poachers versus predators and then validate it with a very little labeled data set. So what am I trying to get to is, primarily, I think, for this community standpoint, I think a data collection standpoint has been addressed. Things like delay tolerant networking, which did come out of MobiSys, in fact, compressive sensing. These are some of the challenges that I think to a large extent have been addressed. If you look at the platform that was used to collect data, location data and accelerometer data from the Rhinos and from the monitoring the Rhinos, this was done using a LoRa network, which I would say 10 years back was still in the research stages. Today, it was a full-scale LoRa deployment, which was working for at least 2 years today. So where do the challenges lie is in terms of the AI and ML model learning. Some very interesting challenges arise when you start looking at IoT in the wild, because it's very difficult to collect labeled data. And when you start creating models, your models have to be on limited data or from learnings from other fields. In this case, what I've shown is using behavioral scientists, taking their input and then being able to take that and then create your model. And then in the other case, it was about taking the physics based simulations, n-body gravitational simulation models, and then being able to integrate that with spatiotemporal indexing. And how do I basically create any AI or ML model that will take in a very, as much as possible, an unsupervised fashion? So once that is done, these are all events that change dynamically in time. You know, if you look at environment, you know, the way animals' behavior is not going to change, but it's also going to evolve over time. How do you account for the changes in the model that I have built once it's deployed in the wild? How do you do incremental training on evolution, and then also, you know, real-time prediction? So these are, to a large extent, open problems, and I believe that there is a lot of scope when you start looking at machine learning models and deep learning models. And I know that a lot of us have been talking about deep learning, but what is the one fundamental problem that, say, deep learning or any machine learning poses for IoT data is that it has to be, you know, take into account unsupervised nature of it. It has to be able to work in the wild. You know, when I deploy it, I forget about it, and I need to be able, it has to be some kind of a self-learning device essentially. So with that, I will, you know, end my talk and just say that there are a lot of people that I need to acknowledge. It's not just my efforts, it's a lot of people who have worked in this space, and including my own teammates and other university partners. And we also had a lot of funding from Army Research Labs for doing some of the basic fundamental scientific research in this space. And of course, you know, being from IBM Research, that's a great place to be doing this work in.